Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I'm happy to try and both address specific questions and talk about general topics. I see that there are all kinds of questions left over from before. Let's see, where should we start? Start with one from Wave. The question is about large language models like GPT-3, how they work and how to ask the right questions. Okay, so let's talk about what this is all about. So in the modern world of artificial intelligence, AI, and machine learning, one of the areas that's been very popular is dealing with human language. And one of the ideas, the idea of things like GPT-3 is it is a particular example of a neural network that has been trained to generate natural language. And it's essentially the way it's working is that it's been given billions of examples of if this piece of text, of different pieces of text, and it's trying to learn from examples. So it says, if the piece of text said the earth is, I don't know, round or something, let's say the earth is blank but not flat and not flat, then there's a very good chance that in all those examples of text that it's picked up, that there'll be quite a few that say the earth is round but not flat, let's say. So what is going on is this neural net is learning from examples what are typical words that get filled in typical places. And so what is being done is there's lots and lots of text, particularly from the web. There's a few billion pages of text on the web, for example. I'm not sure, but that's specifically where GPT-3 was trained. But there's lots of text out there and available in the world. And so the question is, can you have something that learns from those examples and tries to reproduce things that are like those examples? How does it work inside? Well, it's essentially what's happening is it's making kind of a program that is set up so that it says, if you've seen this, then the chances are you will see that later. So for example, how would you make such a program? Let's take it at the very simplest level with English. If you see a Q in an English sentence or an English word, there's a very good chance that it's going to be followed by a U. If you see a TH, for example, there's a decent probability that it's going to be followed by an E with the word the, for example. There might be some other things that might be followed by. So the very simplest thing one could imagine doing is just trying to learn, given a letter, what's it most likely to be followed by. In the case of Q, it's rather obviously U. In the case of other things, it might be different probabilities for different letters. So the first thing one could do is one takes a big sample of English and one just looks at every letter and one looks at what follows it. And that gives one a thing that will tell one the chances are, if you have a Q, it'll be followed by a U. So now if you're in it trying to use the system to generate a word, for example, if it generates a Q, then it pretty much knows it's going to put a U after it. So you can generalize that idea by working out if you see this particular word, it's most likely to be followed by this word. In the model that gets made, the program that gets made to decide what follows what is much more elaborate than that. It tends to be, it's based on neural networks, which are essentially taking, how to best explain this? You can think of it roughly as you are seeing a set of words or characters, and you're kind of probing different places. So let's say you've got a piece of sentence that is 50 characters long. You've got something that's, think about it like kind of a creature with lots of tentacles, and different tentacles are connected to different letters. And what's happening is it's kind of if you say letter number 3 is connected to tentacle number 5 or something, and it's kind of when it notices, when that tentacle notices that that letter is an A, then it says it produces some kind of signal And if some other tentacle notices some other letter is something else, it produces some other kind of signal, and you're kind of learning how that collection of signals put together, what that is likely to mean should come next. And as I say, the details of how this works are kind of complicated, and in a sense very messy. They're typically several layers, many layers of kind of this is sensing that, and then you sense from the layer, and then you sense from that layer, and then there's more elaborate things where you have sequences of things where one thing will produce other things, and you pay attention to what's happening later on from that sequence that's produced, and so on. It's really quite complicated, and it's not something where humans in detail understand what's going on inside. What's been done is people have found sort of methods for grinding up the data and producing predictions about what's going to happen, and those methods have sort of just empirically been found to work. And then people feed them just huge volumes of examples, and gradually what's happening is that one is setting up those programs to sort of follow the examples as well as they can. Okay, so the end result is, what should happen is you ask it a question, like you might ask it, how does GPT-3 work? And its goal is to start producing text that represents the answer to that question. And it's going to do that based on the things that it's seen before. Now, how well does it do? You know, some people would say it does fantastically well. Some people would say it does terribly. Somebody produced for me recently a training of GPT-3 that's based on things that I've written and I've said, and transcripts of these live streams and so on. And I have to say that what it produced seemed to me terrible. Didn't sound like me at all. It sounded like the thing was sort of aimlessly producing sentences that I felt like other people's sentences, not my sentences. So I wasn't very impressed. But that's kind of the idea, is sort of regurgitate what you have seen before. And in terms of you know, asking questions where you're likely to be able to get an answer from it, well, if there is something where out there in the examples that it's learned from, there was this question, this answer, then it's a good bet that it's going to be able to respond in that way. Okay, very different question here. Brian asks, dangers of space junk around the Earth posing a risk to commercial space hotels and so on. Well, I don't know how many objects there are exactly in orbit around the Earth. I think maybe a few 100,000 probably now, including some tens of thousands of satellites and some number of sort of disembodied bolts that fell out of satellites and things like this. There is, all of these things are tracked. It's pretty easy if you have a metal object, even quite a small one, it reflects radar much better than other things. And so it's comparatively easy to track all the stuff that's in orbit around the Earth. And one of the things that is certainly an issue, for example, there have been a few incidents where, well, there have been few incidents where people have tried to sort of blow up satellites with lasers and things like this. There have been other incidents where, not too many, but some, where satellites have collided with each other. In those kinds of cases, lots of pieces of stuff get thrown out into orbit, and you have a lot of sort of pieces of junk that are in orbit. Now, you know, a satellite goes in low Earth orbit at least at 17,000 miles an hour around the Earth. So if you end up with two satellites that are in different orbits and they cross over and they collide, they are colliding at a very high speed. And so the amount of, so they'll tend to produce lots of junk. Now, what tends to happen is that something which is in orbit around the Earth will kind of stay in that same orbit. The orbit, if it's low down to the Earth, like let's say 50 miles up or something like this, if it's low down to the Earth, the orbit will steadily decay, because what's happening is there are kind of wisps of air from the atmosphere that kind of reach up into space, and those will tend to collide with whatever is orbiting, and that will gradually cause the orbiting thing to lose its angular momentum and to lose speed and to gradually decay into the atmosphere and probably eventually burn up in the atmosphere because because as it starts to go into the thicker parts of the atmosphere, what's happening is you've got a thing going at I don't know, 25,000 miles an hour, let's say, as it falls towards the Earth. And that is something which, as the air flows around it, it'll get very hot from all of the collisions of air molecules with that object. And that's why, you know, when spacecraft re-enter the Earth's atmosphere, they have to have these elaborate heat shields, usually made of ceramics and so on, that protect them, because the outside of the spacecraft it's being bombarded with the air at very high speed, and that air is it's the same mechanism as friction. If you rub solids against each other, they'll get hot, and it's the same basic mechanisms that's happening where a very fast object falling through something like air also gets hot like that. So in terms of people certainly worry about the increasing amount of junk that's in orbit around the Earth, and you can start worrying about these kind of streams, these areas, these sort of tubes of debris. If some satellite blew up, there'll be some place where so when it blows up or when something happens to it, there'll be things that are just going in the direction of the orbit. And then if the thing explodes, then the force of the explosion will cause some of the pieces to be not quite in the same orbit. And so you'll end up with this sort of tube of stuff that is in some range of orbits going around the Earth. And the question is, if you are in the way of that, that's bad news, so to speak. And there are, so people, how rapidly that will build up, I'm not sure. I think the thing that people always worry about is that if a bunch of debris builds up, then it will be the case that the chance that a given satellite will be destroyed by debris goes up. And then when that satellite is destroyed, it will produce more debris. And so it essentially produces a chain reaction of debris where more and more debris is produced, and eventually it's you're kind of dodging bolts all the time if you want to be in Earth orbit. I think we're far away from that situation right now, and there's sort of questions about what to do about it. I know there's at least one company I ran across where they're interested in providing essentially salvage services in orbit, where they're going to send up their own satellite that can kind of maneuver around and try and pick things up and so on. And there are various initiatives like that. I mean, there's also the question of can you zap, if you know that there's a bolt in orbit somewhere, can you zap it with a laser, for example, and let's say even vaporize it and cause it to then not be harmful to other things. That's also a possible thing to do. You know, there's a question here. The question here, it seems like science literacy is on the decline. What can we do about it? What does it mean to be scientifically literate? I'm not sure that science literacy is on the decline. I think there's more and more known in science, and so there's more and more to learn. I mean, I've noticed in the course of my life that the general awareness among people that there are things to know in science has definitely gone up. And the importance of knowing things in science has definitely been something that people view as being more worthwhile, I think, because more and more is being said on the basis of science that affects people's everyday lives, which wasn't always the case. But in terms of what sort of is scientific literacy, what does this mean? I would say that obviously these live streams that I'm doing are my attempt to kind of transfer whatever scientific literacy I might have to other people. And I think sort of the core, in a sense, of scientific literacy is probably knowing stuff about science, knowing sort of facts about science, knowing what's been discovered in science over the years. I think that that's, and across lots of different kinds of science. And some kinds of science are very much sort of on their own, some really connect to others. I would say that getting to the point where when you in some areas of science, there's a certain amount of jargon that you have to know. Otherwise, you just really can't understand what people are talking about those areas of science. I would say one place where that gets one common place of interest to people is medicine, where there tends to be a fair amount of jargon. And as soon as you know a decent amount of that, you can immediately understand a lot more. And without that, you're kind of somewhat locked out of that. I have to say, it's one of those cases where, having learnt Latin as a kid, that's super useful in medical jargon, because most of it, actually, some of it hasn't changed since the time of writers like Galen in antiquity, writing about these things. And in some sense, when you hear one of these pieces of medical jargon, you don't understand it. If you remember words in Latin, you just translate from the jargon is just a piece of Latin, and you can translate it. But so, learning the kind of the facts and jargon, the basic facts and jargon of different fields is really worthwhile. I'm not sure I think then a certain degree of mathematical literacy is useful, because it's like, oh, there's this percentage of that, and there's this chance of this happening, and then if there's a chance of this, and then there's another, given that there's a chance of this, how do you combine probabilities? Those kinds of things. Those are worthwhile. And I would say that the things that perhaps, some of the things that are worth knowing in science are things that are really quite unobvious from everyday experience. I mean, the famous one from 500 years ago was the fact that the Earth goes around the sun, not the other way around. And that was something that, from our everyday experience, that's just hanging out on the Earth and seeing the sun, travel through the sky and so on. That's not obvious that that's the right way to think about things. But that's something that kind of was delivered by science, by Copernicus and others 500 years ago. And it's something where not obvious, but that's something that science can tell us, and that it's something we have to kind of know from science. And so there are a bunch of things like that that are sort of not obvious to us. There are things about the universe in the large, things in the small. There are things about mathematics. There are things that are sort of surprising about the way that, let's say, probabilities combine and so on, that you kind of have to learn as a matter of learning science. In a sense, in the course of our civilization, it's taken centuries often to learn these things. And there are things, those are not things that you can immediately absorb from your everyday experience, just as other people weren't able to absorb them, and it took centuries for scientists to discover them. So it's worth kind of giving yourself the sort of leapfrogging of those centuries by just learning what's already known. I think when you get to the sort of more advanced levels of this, having kind of computational literacy and being able to use like our computational language to just say, hey, I've seen that there's this data on this thing, I wonder what's actually true about that, and to be able to actually, with your own sort of fingers, figure out what's going on. That's, I think, when you really get to a high level of kind of scientific literacy, is when you can go from whatever the raw data about something was to making your own conclusions. But that's a fairly high level of scientific literacy. I would say the other thing that I notice is almost, in addition to literacy, is kind of scientific judgment. What is likely to be true? What is likely to be even known whether it is true or not? These are things where people, I think, often get quite confused about what might be knowable, what might not be knowable. They'll see some headline that says, scientists say, blah, blah, blah. And to somebody who kind of knows science and has reasonable science judgment, you're rolling your eyes and saying, no, scientists can't possibly know that. That headline has to be nonsense. And maybe it's an overclaimed headline, or maybe it's a confusion of some kind. But it's a question of getting a sense of what is knowable and what is not, and what kinds of things might we have data, knowledge about in the world, and what might we not. For some reason, I'm reminded of a question which was right on the edge that one of my kids asked a long time ago, which is, when there were dinosaurs, could the Earth have had two moons? And I realized that I didn't know. And I know enough about how one works out things about the dynamics of planets and so on, that I knew that for maybe 10 million years in the past and 10 million years in the future, you can kind of do mathematical calculations to trace the orbits of planets. And you can know that nothing too funky happened in the solar system over that period of time. But if you ask me for 65 million years, I knew that I didn't know that. The question is it knowable? Could somebody actually have worked that out? I wasn't sure. And in that particular case, I asked, over a period of quite a few years, I asked all kinds of different people who are experts in celestial mechanics and other kinds of things. And I think the general conclusion was, when I began asking it, it was like, we just don't know. And later on, it became, well, now we've been able to do computer simulations of the solar system for longer. And really, it's quite implausible that the Earth had 2 moons 65 million years ago. But if you ask about 2 billion years ago, we just don't know. And this is something where that's an example of something that's very much on the edge. Now, if you say, if you pick all kinds of weird claims, I don't know, let's pick a claim. Let's say, let's have a claim, really the whales have a giant civilization at the bottom of the Pacific Ocean, and we just have never found out about it because they didn't want us to know about it. Is this a plausible claim or not? How could we figure out whether something like that is even conceivable or whether it's just totally bogus, so to speak? Well, so first thing we have to know, for example, one question would be, have we mapped the whole ocean floor? Have we visited the whole ocean floor? Well, mapping the ocean floor is not so difficult because we have, we can use sonar, for example, to, we produce some sound in water, goes through the water, it bounces off the ocean floor, comes back up, we measure the amount of time it takes, we can make, we can figure out things about the depth of the oceans. We can also do that the more directly, even in shallower oceans. People did that from a long time ago. If you literally just have a cable and you let the cable out and you wait until it hits the bottom of the ocean and you see how far that is. And so the question of, have we mapped the bottom of the oceans everywhere? Yes, the answer is yes. There are good maps of sort of the terrain at the bottom of the ocean. Have we been there? Not to most places. It's difficult to get. You have to, the technology exists, but people have been to the lowest points in the ocean, the Marianas Trench, but it's a rare thing to do and it's not something commonly done. And if we start asking questions about, well, it's an interesting one to try and sort of unpack, is how would we know? For example, sort of related to questions about, how do we know whether, take, I don't know, dolphins, whales, whatever, they have all kinds of sounds that they make. What are those sounds? Are those the recitals of poetry? Are they just are they like bird songs just being produced apparently just to show that they're there, kind of thing? What are they and how can one tell? Well, those are actually pretty difficult questions. And I don't think if somebody said, actually, the whales have developed epic poetry and they're reciting it across the Pacific Ocean, so to speak, because sound travels a long way in the Pacific Ocean, I'm not sure that it's easy to refute that claim. But I mean, let's see, what would be some other things that people might claim that, oh, I don't know, they're questions like, what would be a good example? What's a good example? But let me say that areas where there are different kinds of scientific knowledge that have different degrees of certainty. So for example, let's say in mathematics, you say the following relation is true: 3 squared plus 4 squared equals 5 squared. Okay, well, immediately you might not know if it's true or not, but you can clearly work that out and you can determine definitively, yes, it is true. And that's a case where there is a very high degree of certainty. Now, if I say to you, for example, every even number is the sum of two primes, okay? You can say, well, let's take the number 8. It's equal to 5 plus 3. Okay, great. That's 8 is the sum of two primes. Let's take 20. We can work out what it is. It's 17 plus 3. It's again the sum of two primes. And we keep doing that. And we keep checking, is every number the sum of two primes? We'll discover in that particular case that yes, we can keep checking. We can keep checking for trillions of numbers, and it always seems to be true that every even number is the sum of two primes. Do we know if it's really, really true? Well, that's been a thing called Goldbach's conjecture, and it's been an open question for about 300 years, whether that's true or not. People are getting closer and closer to finding a precise kind of logical proof that that is always true, but we don't know for sure yet. And it's still possible that there's an even number out there that isn't the sum of two primes. So that's a sort of, there's a high degree of certainty, but it isn't absolutely slam dunk certain. I mean, there's an example of something a bit like that. You can estimate actually the density of prime numbers, and the so-called prime number theorem tells one that roughly the density of prime numbers goes down roughly like the logarithm of the size of the number. So as prime numbers, remember, are numbers that you can't represent as products of other numbers. So for example, just like you can say, I don't know, 10 is 5 times 2, it's not a prime number. 11, the only thing you can say is 11 is 11 times 1. There's no way to break it up into two numbers that you can multiply together that will get 11. And so if you go through and look at different numbers, you'll find that there are lots of prime numbers, and the density of prime numbers, the chance that a number is prime, gradually goes down as the numbers get bigger. That's sort of not surprising. It's kind of like, well, there are more ways you might be able to make up the number from smaller numbers as the number gets bigger. And we know, one thing that was proved by Euclid actually in antiquity is that there are an infinite number of primes. We don't know, for example, another thing, talking of certainty, twin primes like 11 and 13, which differ just by 2. There we found lots and lots of twin primes, but it's still not known, even after 2,000 years, if there are an infinite number of twin primes. We know there are an infinite number of primes altogether. We just don't know whether they can always, whether there will be, whether forever we'll keep on getting infinite twin primes. So it could be the case that the density of primes becomes so low that there are no longer twin primes anymore. But it seems unlikely, but it's not a proved fact at this point. By the way, even when we talk about things where we say it's proved, it's established, it's mathematically established. Well, in setting up mathematics, we always have to start from certain kinds of axioms. We have to start from things like we say, it's always true about addition that A plus B is equal to B plus A, that addition is commutative. It's always true that this or that. It's always true that if you can prove something about n from the thing about n minus 1, that you can keep doing that. That's the idea of induction, that if you can prove something from a thing about the case of n from the case of n minus 1, and you can prove for the case of 1, then you can prove it for all n. There's a collection of axioms that you provide that is the sort of raw material from which you build up your mathematical ideas. But then one of the things we know from Gödel's theorem from 1931 is that there are things which you can write down that seem like they're questions about, let's say, arithmetic, like are there an infinite number of twin primes? Is Goldbach's conjecture about primes true, and so on, but which the axioms of arithmetic, as we know them, as we write them down, are not powerful enough to prove. So those things there's no way, just from the things that we have defined to be the way that we set up our mathematics, to establish those facts. So that's a bit about sort of certainty in mathematics. There are many things where you can definitively say, yes, this is, I can calculate it, it's true, or given the axioms that I'm assuming for my mathematics, I can prove by logic that this is true, so I'm done there. So now the question is, well, what about natural science? What about things about the world? Well, it gets much more complicated because we don't have an intrinsic way to know how the world works. The world works according to natural laws. In physics, for example, we are pretty confident that if we make a carefully enough designed physics experiment and that we do the experiment once, we do it again, we'll get the same answer every time in some sense. There are many footnotes to that issue having to do with quantum mechanics, for example, where we only can apparently work out probabilities. In fact, a lot of this gets very much informed by our recent work on fundamental theory of physics. I think we can now understand why it is that there is sort of uncertainty in the results of experiments that we do in physics. And it really has to do with us as observers sampling this kind of infinite thing, which we call the Roolead, which is this kind of this infinite entangled collection of all possible computational processes, in a sense, all possible histories of the universe. And the question is, which of these do we sample? And the answer is, there are particular ones that we're sampling by virtue of the way that we experience and our senses experience the universe. The particular, and it is that sampling of this ultimately completely determined collection of all possible histories. It's our sampling of that determines what we actually perceive in physics. And so that's so there's sort of in a sense, the uncertainty about what happens has to do with, well, how are we looking at it, more than in some sense what's ultimately really there. But it doesn't do us any good to say, well, in principle, there's this Roolead thing that is the sort of the set of all possible physicses and so on. That doesn't really do us any good, because what we care about is what we experience in the actual physical world with our methods of perception. And that's the specific laws of physics that we have. But so in physics, there's, when people say, well, such and such a thing has been discovered, et cetera, et cetera, et cetera, there's a certain degree of solidity to that, but it's very tricky because, when somebody says, we've done an experiment, it was a really hard experiment, we got the following very unexpected result. Is it right? Is it not right? For instance, for a while, people said, this was in the 70s, I guess, 1970s, people were worried that the sun might have gone out, that the sun might have stopped, that the center of the sun might no longer be producing energy. Okay, why did they say that? Well, and I'm sure there are a bunch of sort of trashy newspaper headlines along those lines. The center of the sun is like 10 million degrees centigrade. It's and when you produce light, photon, heat at the center of the sun, it takes like 1 million years for the thing to get to the surface of the sun. And because it keeps on, the sun is not transparent, and it's like that piece of heat keeps on getting from one, it takes it a long time to kind of diffuse through the layers of the sun. But that's not true for neutrinos. Neutrinos are particles that interact very little. So it's very typical for a neutrino to go all the way through the Earth without interacting. And in the nuclear reactions that happen in the sun produce neutrinos. And so one of the things people expected is from the center of the sun, there will be all kinds of neutrinos being produced that would get to the Earth. And if we were clever enough, we could detect those neutrinos on the Earth, and we could even sort of, in a sense, X-ray what's happening, neutrino ray, what's happening at the center of the sun. But in fact, no neutrinos were observed coming from the sun. And it's like, oh my gosh, what's going on? And so there were all kinds of theories about the reactions at the center of the sun, and there was maybe the sun has gone out. That would be very bad. Eventually, I mean, it would take millions of years probably for the badness to sort of diffuse out. Or maybe there was something wrong with the experiment. As it turned out, there was something wrong with the experiment. It was a difficult experiment where you're kind of looking for flashes of light in these giant tanks of fluid that are in mines deep under the Earth, et cetera, et cetera, et cetera. And you have to kind of calculate, if a neutrino goes through in this way, how would the flashes of light be produced? And it wasn't quite done correctly. And there wasn't really a test where you could say, well, we know that this produces neutrinos in this way, and so we can test whether we kind of know the apparatus is working properly and so on. So that's a place where even the finest physics experiment just got the wrong answer and concluded something strange. Now, there are other things that people, like, for example, when people first discovered that the universe was expanding back in the 1920s, I guess, that was a very surprising claim. It turns out those experiments were not terribly hard to do, and it was pretty easy to determine that, yes, that really was correct. Now, in more recent times, people say the universe is expanding a bit more quickly than you would expect. And that's leading to all kinds of theories of dark energy and negative mass matter and all kinds of things like this. Is that correct? Is it not correct? It's a tricky issue. It's a tricky issue having to do with looking at, supernovas, exploding stars, having to figure out things like, is a supernova that exploded in the first billion years of the universe, does it produce the same amount of energy as a supernova that explodes today? How does one confirm that? It's very hard to confirm. So you have to have these kind of nets of theories that say whether how you interpret these experiments and so on. So it again gets quite tricky to know whether the experiments are right or not. And there are things where there've been in the history of physics that I've known it. There've been several kinds of things where people regularly, every decade or so, they'll say, "We found this effect. We found this particular thing," and turns out it isn't correct. One of the things that I've sometimes used as a heuristic is when somebody says, "I found this effect," and nobody ever imagined that it could be there, I give it an uptick in whether I think it's likely to be true. Because in a sense, if you see something that nobody ever thought was going to be there, it's not like you are setting up your whole experimental analysis and so on the basis of this is what we're going to see, now we confirm it. But anyway, even in physics, it's often hard to know, and one slowly gets an intuition for what kinds of things are like, that's a slam dunk. It's easy to tell that experiment will be correct. I don't know, when the Higgs particle was discovered, for example, in particle accelerators and in collisions of high energy protons and antiprotons, you could look at the data where there was some thing of a certain mass that was produced. You could look at the data and I don't know, somebody like me who's probably seen a lot of this kind of stuff before could pretty much say, yeah, it's probably right. That's a sufficiently clean signal that it's probably correct. There are other cases where sort of things are seen where you look at it and you're like, the data is wiggling around all over the place. Is it really going up? Is it really going down? Is there really a bump there? Very hard to tell. And you kind of know, if somebody is claiming something big on the basis of this data, it's kind of like, well, maybe, probably not. If you go outside of the physics, things get much more difficult. Because, for example, in biology, one of the issues is that sort of every organism is different. All of us people are a bit different. So, and even, different days will behave differently. And, if we say, this particular drug has this particular effect on us, or this particular, vaccine has this particular effect on us, well, it's going to depend on the person, because we all have slightly different genetics. We have slightly different, we've grown in slightly different ways. We've eaten different things. We've had different experiences and so on. So no two are the same. And so it's much harder to do kind of a controlled experiment where you can say, this is what's true. Everybody who eats this is going to have this happen. Well, it's not the case. There's a distribution of outcomes depending on the person. And it can be very confusing because it's like somebody will say, this thing has some wonderful effect. Okay, it's a wonderful effect, but only on 10% of people. But if you know what is special about those 10% of people, then maybe on those people, 90% of the people who you can identify as having that special feature, it'll have a wonderful effect, and so on. But it's kind of like, first thing is, when you hear some kind of claim about all this, do that in biology, you have to kind of read the fine print It's also the case that people will do sometimes, oh, I don't know, they'll say, what's a good example? There's all sorts of shocking examples, but okay, here's one. I don't know. I haven't seen a particular study on this, but I'm sufficiently certain. Here's an example. Example would be people in certain Western countries have higher IQs than people in other countries. A claim somebody might make. Okay, well, let's unpack that claim. What do you mean by IQ? Very dubious concept to begin with, but you probably mean somebody did, an IQ test. Okay, well, people in this country have probably been to school and they've seen all kinds of tests that are just like that. People in some other country, their school works differently. They don't go to school in the same ways. They've seen different kinds of things. But the conclusion, the original stated thing was, people in, country X, Western country X, have higher IQ than people in whatever. Okay, that claim is no doubt bogus. But the reason it gets that way is because the people are better at doing tests that they've seen examples of before. People are, and so it's sort of a self-fulfilling prophecy, because if you say, well, we're going to test the things that people have learnt in this system of education, then it's kind of unsurprising that they will do better in those tests. Now, can you roll that back to make the conclusion they have a higher IQ, whatever IQ might mean? Well, of course, if your definition of IQ is they do better on this kind of test, then the answer might be yes, they do better on that kind of test. But you might, from the headline, you might say, oh, that means that their brains work better in some way. Undoubtedly not true. And so that's the kind of thing where it's like, I would say the scientific judgment is, what does this claim mean? Could it possibly, is there some trivial reason why it might be true? What kind of measurement could possibly have even been done to establish it, and so on. So I think those are kinds of things that are useful in sort of testing one's scientific judgment. Is, you see these headlines and you ask the question, could this possibly be true? Does this mean what it says it means? Does it mean what the person who wrote it thinks it means even? Does it, and it is, I think that sometimes science is just hard and people get the wrong answers. Sometimes the science is terrific, but people will then take that sort of scientific claim and through misunderstanding or trying to achieve some particular purpose will turn that into, oh, there's some dramatic conclusion that can be made on the basis of that. And look, it's backed up by the science over here. I'm sometimes shocked at some of the things that I've invented in science, where I see people saying, oh, this means that. And it's like a pretty common one is things about the universe is a computer and we must live in a simulation, which is completely not the conclusion or even the correct way of thinking about a lot of the science that I've done. But that's something where people have kind of a very common trend, a very common trait, is people will take something about science that may be a little hard to understand, and they'll kind of drag it into something which is as close as possible to terms that they understand. And sometimes it breaks it to do that. Sometimes the science is a bit more subtle and it doesn't just fit into the kind of the rubric, the framework that one knows, for example, from everyday experience. So that's another kind of phenomenon. I would say that one of the things about sort of scientific literacy and getting it, so to speak, is this concept that people, I hope some of what I try to do in these live streams supports that, is like, you can actually figure stuff out. You can actually think about things. It's not the case that all science, for example, is just delivered by scientists and you don't get to, and it's just a pure sort of thing that arises as kind of a sort of a kind of a text that's just delivered in its final form, and this is true, and that's all there is to it. If it is the case that something is presented scientifically, you should be able to unpack it, think through it, know why it's true, know, even if you don't, well, in some cases, if you ask some question about physics, why is energy conserved in physics? Well, I think I am beginning to know the answer to that on the basis of our fundamental theory of physics, but that's not something that people have been able to to answer that question why before. But there are many things at sort of not at that foundational of a level in science where you can absolutely say, why does this work this way? Why is it the case that, oh, I don't know, in some biology, medicine, engineering type thing, why is it that that this thing happens? You should be able to explain that in terms of sort of more general principles. So I think another thing to say about sort of explanations in science is you've got a particular phenomenon. I don't know, clouds are white, let's say. So you could explain that phenomenon just what does it mean to explain that phenomenon? What it means is you are sort of going down to a lower level and you're saying, well, clouds are made of water vapor. Water vapor has these characteristics. Light has these characteristics going through water vapor. You're going to a higher level of generality in the explanation. So in other words, clouds are one thing that's made of water vapor, but water vapor occurs in other places and other gases occur in other places. So you're going from the particular of why are clouds white to more general principles. And the essence of scientific explanation is to go from the most general principles you can to the explaining the particulars of what you're dealing with at that particular moment or in that particular question. So I think and sometimes when you get to those general principles, you eventually reach the point where you say, we don't know why energy is conserved. We just know that it is conserved. We don't know why this or that thing is true about physics. I have to say in physics, we're beginning to, I think, have a lot of good explanations for those things in terms of sort of ultimately in terms of formal mathematical kinds of deductions that are things which we can say must be true. They're not things that are, well, those things must be true. The particular ways that we sample and observe those things, that's a slightly trickier issue to understand that has to do with the particulars of how we we perceive things and so on. But so I think in some sense, when you say, is there a scientific explanation of this? What you mean is, can you go from the particular phenomenon down to something which is based on more general principles? So if you take examples in biology, medicine, why is it that this, I don't know, disease works this way or this medical phenomenon works this way? To just say, well, it works that way because it works that way is not really good enough. To be able to say, well, it is that way because of some feature of molecular biology and something about, proteins of this type have this kind of property and this and that and the other. By going to those more general principles, that's what it really means to have a scientific explanation. And I think that sort of in some sense, scientific literacy perhaps can be thought about in terms of, do you know those principles? Do you know those underlying principles? And to what extent can you successfully reason about things and sort of bring them down to the level of those principles? And again, it's and sort of a good test case, I suppose, are these things about, is this science headline, plausible? Is it even knowable? Is it is it something where we could, in the current state, if somebody says an ad for a breakfast cereal has been spotted on a planet orbiting another star. Very implausible claim, but that claim, one could know, is not a claim that claim couldn't possibly be true in the current state of our knowledge. Telescopes just do not exist that have the resolution to be able to, read the ad, so to speak, on, a planet orbiting another star. Now, could you build such a telescope? Interesting question. Or, could somebody say in 100 years, could we do that? Well, then you have to know some more things, and you have to know about sort of the criteria what limits the resolution of telescopes while on the surface of the Earth. It's limited by the atmosphere to a large extent, but ultimately it's limited by the size of the telescope compared to the wavelength of light and so on. And so you can imagine you build a big enough telescope, you can in principle see very arbitrarily high resolutions, but it becomes more and more challenging to build that bigger telescope. But I think, I mean, I was going to say that one of the things that I think is sort of a big enemy of science literacy is kind of sort of science as delivered fact, so to speak, where it's just like everything about science is just like, learn this fact, learn this fact, learn this fact. Now, knowing facts is super useful, but believing that there is no way to unpack those facts is a mistake. And I think it's, as I say, it's a good thing to sort of wonder about this or that question about science and just say, do I know principles which would allow me to make conclusions about that? Another thing that can happen, it's happened a lot in these pandemic times, for example, is people quote numbers and they say, oh, there have been this number of cases and this number of hospitalizations and this number of thises and that's. And one of the challenges is to unpack what those numbers really mean. So for example, somebody might say, there have been a lot more cases in the US than there have been in Australia. Okay, it's like, oh my gosh, something, the US must have done something bad or something. Well, of course, the first thing to realize is that the population of the US is what, 350 million or something. The population of Australia is what, I don't know, 25 million or something like that. So it's, there's a, to say that there are more cases in the US than in Australia is like, well, what is probably the more interesting question is number of cases divided by population. What is the chance that any given person would get sick, for example? So that's the beginning. But then you can ask questions, when you see these numbers kind of all packed up into, oh, this number is the fraction of people who had this or that and so on. It's always a kind of a challenge to see if you can unpack those numbers and see what did those numbers really mean. Now, sometimes numbers are only quoted in some kind of combined form, and you actually can't deduce the thing that would be the really interesting thing to know because people have quoted those numbers in a certain way. So it's so anyway, that's sort of another piece to this whole kind of scientific literacy thing is understanding how to unpack these numbers. And very often, really all it is dividing numbers by other numbers and knowing, a percentage increase, what that means. Just sometimes it's more a question of if X percent of these people do this and Y percent of those X percent do this, what does that mean, do the combined thing and so on. And then it gets a little bit trickier. And sometimes you have to know rules for combining probabilities and things like that. And there are some slightly tricky mathematical results about combining probabilities that often get kind of confusing. Well, okay, so that was a little bit on scientific literacy. I think, as I say, my main statement would be there's a lot that sort of, if you know a certain set of scientific facts, there's a lot that you can kind of unpack and figure out for yourself. And just to read the headline and say, oh, scientists have said X, it's like there's subtext below those headlines in all fields. And the kind of the way to really be scientifically literate is to be able to get down to say, could that be true? Why is it true? What does it mean that it's true? And so on, rather than just like, oh, another fact. It's and there are things where sometimes I remember when people first claimed that the dinosaurs were killed by an asteroid impact, that there were things about that might at first have seemed completely implausible. But as you dug a little bit, you realize that, well, actually, like there's a thin layer iridium, I think, sort of ash that coats the Earth at a certain depth that corresponds to the vaporized asteroid that hit the Earth 65 million years ago. And when that's observed in different places around the Earth and so on, that becomes somewhat convincing that that really did happen that way. But it seemed very implausible at first. But it's one of these things where, is it plausible? Is it not plausible? You dig a little bit, you kind of start seeing whether it's plausible or not. Sometimes also there are, one of the things that can happen is there's a theory. It says a definite thing. Oh, the theory didn't quite work right. So people patch the theory and they say, well, there's also this effect. And oh, there's also this effect. And of course, it happens this way because there's also this extra thing. When it gets more and more shaggy dog like that, it again, the sort of scientific judgment says it's less and less likely to be right. But that's not always true. Like, for example, the current theory of the formation of the moon is this big splat theory. Involves like, well, one thing had to hit the Earth and two things had to coalesce, and then that produced this whole bunch of stuff that then it's kind of like two steps to produce the moon. Whereas you might have thought that the most plausible theory would be a one-step theory, but that's a case where it seems like maybe the two-step thing is right. But if you said it was an 18-step process to produce the moon, then that seems much less plausible. So anyway, let's see. Well, a question here about Dr. Verm. Do you think the scientific process has been damaged during the pandemic, but more because the speed of information opinion on the internet? Look, I think the pandemic has not been a great moment in the history of of credibility for science. In my opinion, the worst problem has been a sort of failure to communicate what science knows and what science doesn't know, and a great tendency to just sort of announce science implies this, science implies that, when realistically, if you know the science, it is not as definitive as that. Now, it's a challenging thing because it's a question of, what do you do with, people who have a range of different levels of, panicking about things and ignoring things and so on. What do you do? How do you best communicate sort of what's known and what's not? My own tendency, which perhaps is more, suitable for me than for everybody, is just say what you know and say what you don't know. And that way, kind of, we're all in it together, so to speak, rather than just sort of announcing this is what's true, or people saying, no, it's all nonsense. That if you can accurately convey what's known and what's not known, and why, go a little bit down to the level of principles for people who care. If you say this is what's known, and I think a larger number of people than one might imagine. I certainly know many people who I would not have expected to be following kind of the scientific details of the pandemic have been following it in much more detail than one might have imagined. And I think that to have provided sort of more levels of well explained science below kind of just this is true, got to do this, et cetera, et cetera, et cetera, would have been a good thing. I mean, I think that there's it's a question of how worried should one be about this? Well, sometimes it's like we don't really know. What's going to happen? Well, we don't really know. But here's what we do know. And I think that in many cases, for people to have been able to come up with, to some extent, I mean, I think there are, for example, people's assessment of risks of different kinds of things for themselves and for other people. Sometimes people are completely crazy about that. They have completely wrong estimates of risk for themselves and for other people. But sometimes they know plenty about their local environment, and they are better able to assess risks than one is from the outside, so to speak. But I think that now, in terms of sort of scientific communication, on the internet and so on, there's clearly crazy stuff that's happened, but there's also good stuff that's happened. There's a lot of things where it's been sort of a question of collaboratively figuring out what's true, and the fact that people, send out a tweet and somebody else responds to that and so on, and it all happens in a few hours is a really good thing. And sometimes something completely crazy is said, and then something else crazy is said, and it all spirals out of control. But there's also been lots of good stuff that's been done by virtue of kind of very people who don't know each other at all, who are just sort of anonymous handles on the internet, exchanging good sort of scientific thinking and coming up with good conclusions. I think that people have had the idea that, there's a gold standard in science, there's a way science knows intrinsically whether things are true or not. And sometimes people talk about peer review of journals and things like this, but there really isn't a gold standard of what's true in science. There are things that get you more levels of certainty, more levels of it's not complete nonsense and so on. But it isn't the case that there's it's a nice illusion typically had by people outside of science that things like the peer review process is going to determine if it's true or not. Well, it doesn't. It's a very imperfect process, like everything. I have to say, for myself, it's kind of like you see one of these headlines, whatever it is, and it's like, okay, do I believe that? I'm going to have my own opinion about whether it's true or not. And sometimes, actually quite often in this pandemic, I've said, let me go and look at the raw data. Okay, I'm able to do that. I can fire up my Wolfram language on my computer and start ingesting data and actually make the plots and see what happens and so on. And it's like, sometimes I'm like rolling my eyes and it's like, whatever, why are people claiming this? This is obviously nonsense based on this data. I have to say, I've tended to avoid saying too much about it, because it's like, I haven't, if you say, did I get it right or not? I'm pretty sure I got it right. I got it right enough that I'm prepared to make decisions for myself on that basis. Did I get it right enough that, I know that I've nailed every single possible effect and I know every possible footnote about what's going on? Well, I haven't done that amount of work. So, that means I'm not going to go and put up a big flag and say, I'm absolutely certain about this, because I haven't done all the work to tell that. I'm certain enough that I'm prepared to make decisions on the basis of what I figured out for myself, at least. I mean, also realistically, unfortunately, the level of kind of politicization and unpleasantness associated with kind of sort of science around this pandemic has been so high that for people like me, it's a major disincentive to actually sort of say very much at all publicly about things, because it's like, oh my gosh, somebody is going to think I'm saying this and that and the other, and that's going to be a huge disaster, and that's not my cause. I'm just I might be interested in what's true. I don't think I have a particular agenda in this is true versus that's true and so on. But people are going to, based on what I might conclude is true, people are going to say, oh, you must be saying that because blah, 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 blah. It's an interesting challenge. I will say something, sort of a personal piece of this is that some of what we've done in our physics project has provided a kind of formalism and approach that that seems to have a bunch of interesting things to say about immunology. And I have been kind of nervous about investigating that, because it's like, I don't know how much we'll be able to figure out, but we may very well be able to figure out things that conclude things about things that are actually relevant for decision making in the world. And I really don't know how those chips are going to fall. I haven't done the science. I don't know what the science is going to say. And it's there are things where I'd say, oh, that's great. It's good for the world. It's a good thing. And there are things where I'd say, well, I wish it hadn't come out that way, but that's where the science led. And I'm concerned, because I think that if things come out in particular ways, it's like people say, oh no, you cooked it to come out that way because you have some whole belief system that's based on that, which I don't think I do. And so it's kind of a bit of a challenge to see how you do that science. And most likely what I'll end up doing is kind of describing to people every step and what's happening. So if the chips are falling one way, what may very well happen, it's very common in science research, is the chips seem to be falling this way for a while, and then you realize, no, there's this other force that's pushing them that way. And as you kind of see these things kind of move around in the process of doing research, you kind of realize that the chips are just going to fall where the chips are going to fall, and it's not something where you're kind of blowing them one way or the other based on some particular sort of agenda that you might have. But that's a hard thing, and in modern times, that's a hard thing to kind of convince people of. And I think that's a disappointing feature of what's happened. But I would say that, to me, the most disappointing feature is the lack of effort to make an exposition of what's going on, and the extent to which, in a sense, it's felt like kind of people are saying, oh no, the public out there, they're just too clueless to understand. We're just going to have to tell them the conclusion. And sometimes tell them conclusions that are, frankly, from a science point of view, kind of wacky, and things where you'd say, well, if you convince people of that, well, you'll probably get them to do this or that thing. This or that thing might be good for the world. But is that really the right thing to do, to convince people of something that is in fact not really right, in order to get them to do the thing that might be the right thing to do? Or is it better to try and tell people the right stuff, the correct, science or whatever, even though that might lead them to conclude, oh no, I shouldn't do this thing that would be good for the world? I think that's a sort of ethics question that I have my own opinions about. I mean, I have to say, I don't think I think it's better to tell people what's known and let them make up their own mind, than to try and kind of nudge them by not telling them what's known, and sort of try and sort of manipulate them into doing this or that thing. But I also recognize that when you run countries and things like this, that's a very difficult, it's a very difficult thing to do. And there are, the tools you have are typically very blunt. And so the fact that that becomes a possible tool to use is something that I recognize might be if you're in the business of running countries, might be something that you feel is necessary, so to speak. I think it's unfortunate, but that's but I'm not in the business of doing things like running countries. All right, let's see. Maybe one more. The question here from Smalls. I can never read these handles. I can't even break them into phonemes. Let's say SMO here. Why is the development of nanotechnology so slow despite its effectiveness in medicine, oncology, and so on? Well, so first of all, what is nanotechnology? So it's been through a bunch of different sort of definitions, but essentially it's making machines out of molecules. We usually, our devices, computers, all these other kinds of things, they're pretty big compared to ordinary molecules. We have in a typical computer, we'll be using 100,000 electrons to encode 1 bit of information. Our whole circuitry for our CPU chip might be, a centimeter across or something, and it's got these billions of transistors, and they're getting down to the scale of limited numbers of atoms, millions of atoms perhaps, but it's not like we are at the level where individual pieces of individual molecules are sort of doing technological kinds of things for us. And nanotechnology is kind of about the story of making machines out of molecules. Now, there is one shining example in the world of where essentially machines are made out of molecules, and that's in biological systems. And there are, you can think of a lot of things. I don't know, the ribosome that transcribes, DNA. It's like this kind of machine that's making proteins and things, and it's just a molecule that exists in all of our cells. And it's something where biology has shown us that it's sort of possible to make machines in some sense out of molecules, but we don't have the ability to to sort of make to order, make a CAD drawing, make a computer-aided design drawing of, oh, I want this machine, it's going to work this way. Now make a molecule that does that. In some sense, that's the mission of chemistry. But chemistry tends to work a different way. Chemistry tends to be to say, these molecules will react in these ways. And it's not really a thing where there may be many steps in a chemical, in some synthesis of some chemical, but it's not something where you say there's a molecule that acts like a machine and has lots of levers and cogs and things in it. It's more like this molecule attaches to this and this atom is pulled away from that and binds to this and so on. It feels like a much simpler thing. So people tried in the 1980s, particularly, there was a big piece of enthusiasm for sort of the take what we can do in machines at a large scale and make it really, really small and make that happen at the level of molecules. And there are lots of questions about, oh, if you have a molecule-sized gear, what does that do? In fact, it turns out some bacteria have essentially molecule-sized gears, the little flagella that are the little tails that propel the bacteria around, that sort of they have to twiddle their tails, and their mechanism for twiddling their tails looks an awful lot like a kind of cogged gear type assembly, and it's just made of molecules. But that's something that isn't, it's not something that we've, it's something not under our construction. And so the traditional view has been that nanotechnology is about taking things that we know kind of work on a large scale and making them very small. Biology didn't really do it that way. Biology has just made stuff that works. In many cases, we are surprised when we discover the things that happen in biology. And I think there's a lot we don't know about how biology sort of fundamentally works. My own feeling is that that is a much better strategy, and this is something that's come out of a bunch of science that I've done, it's a much better strategy to take the raw material that exists in molecules and see how to assemble those pieces to make things that are useful, than to go and say, I know how to make a thing that's useful, and now let me sort of compile that down to make it in terms of molecules. And in fact, well, one of the things that's come out of our physics project recently is kind of a new idea about how to do things like computation at the level of molecules. Typically, people have been thinking about doing computation in the solid state, where all the molecules, where everything is a solid, like the CPU chip of a computer is a solid made of silicon and some additives to that. And it's like every atom is in its place. But the question is, if you're in a liquid, for example, where all these molecules are sloshing around and they can interact with each other, they can have chemical reactions and so on, is there a way to do computation with all those molecules in a liquid by looking at certain attributes of collections of molecules, not just the concentration of some particular kind of molecule, but some other details about how these molecules are kind of sort of bouncing around in the liquid? Is that a possible way to get computations done? I kind of suspect that it is. And that will open up a whole bunch of sort of new nanotechnology-like things, but where the things we're doing they're not immediate translations of things that we've already been doing in sort of large-scale machines. And I think that's a thing there. Now one of the things that makes nanotechnology very, very potentially valuable, in addition to the fact that, well, its molecules are quite small, and so in a very tiny space, using a very tiny amount of energy, one could potentially have a lot of things done if one's doing it at the level of individual molecules. So another thing is that because biology uses essentially nanotechnology-like methodology to do things with molecules, if we want to interface to biology, we really need a kind of nanotechnology solution. If we want to have a thing that's takes piggyback rides on red blood cells, or that goes in and is a little machine that is a kind of a net that goes in front of white blood cells, or let's say T cells or something, and looks, let's say it's a debugger for T cells that tries to figure out, stop that T cell, it's about to attack one of your own tissues and give you an autoimmune disease or something. Stop that T cell, have it have sort of a backpack that pokes it and says, don't attack that tissue, that was the wrong thing to do, and provide that as a piece of technology, so to speak. that's something for which we would have to have kind of a nanotechnology solution that can ride on the back of a T cell, so to speak, to be able to do that. And I think that's that's kind of a big motivation for doing nanotechnology. I mean, I think another thing to say is that something I've sort of often thought, imagining kind of the future of things, is there was right now, we have computers, and there's 100 billion, maybe a trillion computers in the world that are in any car has, I don't know, 50 computers or something in it these days. Any our phones have multiple separate computers in them. It's there are computers all over the place, and but there's still, we think of there being, there's this number of computers in something. Well, if we're able to do computation at the level of molecules, sort of program things at the level of molecules, then no longer will we be saying there's this number of computers in this thing, but rather we'll be saying this thing is just made of computers, instead of it being the case that I have a plastic case for a I don't know, for something that is just an inert piece of plastic. It's like, well, actually, that case is made of computers and it's all programmable. And so, if you want the case to display some weird pattern, it's all a programmable thing. If the molecules can get there, it can be programmed to do that, so to speak. And I kind of think that's the ultimate kind of version of nanotechnology, is it kind of melts into just what everything is made of. That it is the case that in addition to things being computers that are discrete computers, there are also things where sort of the whole molecular structure of something is programmable. So now the next challenge is, okay, so how do you program it? How might you specify? Let's say you've got a thing and it's got a trillion molecules in it, and it's possible to program those molecules to do all sorts of things. How would you specify what you want those molecules to do, and what kind of language would you describe what kinds of things you want those molecules to do? Now, many of the things you want them to do are things which are sort of collective and on a large scale, because that's what we humans think about. Like make the the back of my cell phone case have a big kind of have a giant flashing blue dot or something on it. That would be that's something that's sort of a macroscopic scale that we humans can immediately describe and understand. But something that is on a much smaller scale, maybe it's something we haven't even thought is worth doing, like make that cell phone case, roughen it in this complicated way so that water drops will do this thing on it, so that whatever. It becomes a thing where we didn't even think of that as being a thing you might want to do. And so there's sort of the question, it's kind of an interwoven issue of how do you have a language to describe what you want all those molecules to do versus how do you imagine what you want the molecules to do. And obviously I've spent a large part of my life as a computational language designer. So this is the kind of thing I think a lot about, is how do you define a language that we can communicate with our computers in, and that is a way of describing sort of things we want to have happen in the world, so that they're things that where we understand what we want, but also they're things where we're kind of crispening up those thoughts by providing a framework that is based on some sort of underlying, let's say, computational ideas. So that's a good challenge, is this question of, if you could program everything, if everything was made of computers, how would you tell those computers what to do? And what kinds of things would you say, that what kinds of operations would you expect to be able to do there? And what kinds of sort of conceptualizations would you have of kind of what's happening? We have a hard time imagining what a trillion molecules do unless all they're doing is collectively producing a flashing blue dot. I think that's a thing where it's a mixture of what's needed at the level of conceptualizing the language and what's needed at the level of imagining what's possible. And in a sense, if you were just throwing a bunch of molecules and the chemistry of the early Earth, the concept that life is possible and that you could have living organisms running around live streaming about living organisms and so on, that is possible given only those raw molecules that existed on the early Earth is perhaps super surprising. It would have been hard to imagine. If you saw the early Earth and you were asked, imagine what this could lead to, imagine what kinds of things with these molecules you could construct, you would have a very hard time doing that, I think. And so now, given the technology that we're starting to have, and given ideas like nanotechnology, imagining what could you conceivably construct from this? Let's say the whole Earth was covered with programmable stuff. What could you then do? What would that be like? What would, we could, in a sort of simple way, we could say, well, then we could reconfigure things, instead of having an object where we say, this is a blah, every object, like when we talk about computers are universally programmable in the sense that given a computer, you can feed it a program that will make it run any computation you want. So it isn't the case that we say, we have a computer, we might have a computer that's specially built to be optimized for something, but in general, we have a computer that just does computations. It's not a computer for adding, it's not a computer for streaming videos, it's not a computer for doing whatever, it's just a computer. Now, today, when we think about objects that we hold in our hand or whatever else, we say it's an object for doing such and such, typically. But maybe there comes a time when everything is programmable, where that's no longer the case, where everything is like a universal object, so to speak. And that's, now, obviously, biology has not done that, really. It's done that a bit. DNA is kind of an everything molecule. It can encode anything. Proteins can have many different structures. They're kind of like everything, universal molecules. But when we look at the organization of actual biological organisms, we all have separate organs for doing this and that and the other thing. It's not the case that we have the generic organ that does everything. I suppose the closest we have to things like that, well, brains and the immune system are both examples where they're sort of everything organs that cover, that can be in a sense reconfigured to do, they're programmable, much like computers are programmable, they're reconfigurable. But, it's sort of an interesting exercise to imagine, imagine the whole Earth is covered in completely programmable molecules. What could conceivably happen? What could conceivably be possible? And, imagine that you're confronted with a planet that was set up that way. It's quite possible that the things you would see there would be utterly incomprehensible to us humans, given the current state of our development. It's kind of like, that's an interesting thing that we kind of, have to imagining something that is, what tends to happen in terms of our imagination, in terms of sort of progress in science and technology, is we typically, it's a very incremental thing. We can imagine things that are a little bit in front of where we are today. If we're very good at it, we can imagine things that are a little bit further away. I think a bunch of things that one of the things that's both a good feature and a bad feature is I think I can pretty much say that a bunch of things that, well, I've done the last 40 years or so, and I've worked on are sort of things that most naturally are 50 or 100 years in the future. And that sounds really cool, except for the fact that it's also really frustrating because it's like, look, this is what's going to happen. Okay, world today, pay attention to what's going to happen. Well, you can kind of see, I've been around long enough to be able to see these trends of, yes, the thing I thought was going to happen, yep, it's been happening. But it's kind of like pulling that artifact from the future into today is a very challenging thing, for which it's sort of, I'm, in a sense, perhaps I'm personally more interested in building the artifacts from the future than I am in sort of telling the world today what those artifacts in the future are going to be, although I certainly make some effort to do that. But I think this is a thing where if we imagine, we sort of start imagining the incremental progress. I will say that one of the features of is an interesting story of science discovery, actually. One of the things that's sort of a success story of nanotechnology are these things called buckyballs. named after Buckminster Fuller, and a big enthusiast of geodesic domes, these things that are kind of soccer ball-like shapes where you're making something which is like a bit of a sphere or a hemisphere out of combinations of hexagons and pentagons. But in any case, the thing that people guessed at some point in the 70s or 80s is that you could actually make molecules in which carbon atoms were arranged like the sort of seams in a soccer ball, that you could make a cage of carbon atoms that was arranged in like the pieces of a geodesic dome. And people were trying to figure out, how will we do that? Oh, it's very hard. We've got to synthesize it in this way. We arrange the molecule in this way and that way and the other way. It turns out your average soot that gets produced in a fire has tons of buckyballs in it. It's just nobody knew to look for them, and it wasn't so easy to look because they're just molecules, and you have to have all these techniques of X-ray crystallography and so on to study, the shape of the molecules. But so now it's become clear that right under our noses forever, there was this form of carbon, in addition to the standard ones of graphite and diamonds, there was this form of carbon that was these kind of cages, carbon cages. Well, okay, so that was sort of an early, thought of as kind of an early application of nanotechnology, because there are actually other things you can make out of out of collections of carbon atoms. For example, the other thing you can make is carbon nanotubes, and they have wonderful properties of electrical conductivity and so on, of just these things where you're just making, and they're very strong. They're extremely strong materials. When people have imagined making a thing that you could just lasso satellites in orbit, you could just have a cable that connects the surface of the Earth to a satellite in geostationary orbit, for example. People have imagined that that's a very hard thing to do because you need a very strong material to be able to do that. But carbon nanotubes, sort of woven carbon nanotubes, are sort of the best hope right now for being able to do something like that. But that's a kind of material that is made by thinking about things at the level of molecules and just sort of building this structure that's a little bit like a large scale sort of woven structure, but it's done at the level of molecules. So that was kind of a success story for the concept of nanotechnology. But I have to say that in the first instance, the early kind of buckyball stuff, the main thing I think that came out of that was kind of the non-stick, a new generation of non-stick frying pans and things like this that seemed like a bit of a mundane outcome from such a lofty kind of concept like nanotechnology. But there's more to come, no doubt, with carbon nanotubes and so on. I mean, I would say that this is one of the interesting challenges with science in general is, you know a piece of science, okay, how are you going to use that technologically? You discover that, let's say, let's say you discover there's a material where if you put a magnetic field in it, it will stop transmitting light in the same way. Okay, so what? That's an interesting effect, but so what? What are you going to do with that? Well, you have to then understand, how do you connect that scientific effect with something that has some human purpose that we humans care about? And it's been sort of a strange thing because, for example, if you look at different chemical elements, I don't know, tantalum, dysprosium, all sorts of obscure, well, maybe niobium, less obscure, all these different of the 100 or so chemical elements, that 90 or so stable chemical elements that exist. It's like, well, which ones out there in the world are useful for which purposes? And what's become clear is, oh, well, actually, gadolinium, a somewhat obscure element, oh, that's a really good thing for making very strong magnets out of, et cetera, et cetera, et cetera. And as new technologies come online, whether it's the electric car technology stack with different kinds of batteries and so on, or whether it's computers, or whether it's various kinds of telecommunications types of things, as those different technology stacks come online, so these materials and elements where people are saying, what is this good for? It's kind of it's sort of a that gets discovered because the technology kind of arrives and connects. I find it kind of interesting that there are mineral deposits around the Earth in different places, and some countries got lucky with oil. Some countries got lucky with, with niobium. Some countries got lucky with tantalum. And it's I have noticed, I've been saying this to people from various countries at various times, that if you happen to have big deposits of thing X, then go encourage people to research what is X good for. And I was quite amused that I saw for the first time an ad promoting that for a somewhat obscure from a somewhat obscure element from a particular country. That because it's an obvious thing to do. If your country has tons of mineral deposits of that particular thing, which people say, well, that's nice, but who cares? It's like, if it turns out there's actually technology for which, if you kind of go from the technology end and from the science end, you realize, oh wow, that's an incredibly valuable and useful thing. That's sort of a big win. It's a way of taking something. It's sort of a general thing when you have, in that case, not a science but natural resources, that can you make it more valuable by kind of understanding its connection to technology. All right, well, I think I should wrap up there. So thanks for joining me, and I'll be back again next week. And please do send us. I think we have a way of sending in questions that or topics that we can accumulate through the week, and I will try to address here. And I will say that I always enjoy doing these, because it really helps me to kind of try to explain these various different ideas and concepts and so on. And they're it's very helpful to me. So I hope people find it interesting to hear about these things. And I guess on the live stream chat, we will be taking some feedback and questions for a little while here. I would also like to ask a general feedback question, which is, there are some other platforms that we have considered using to also stream these live streams on. And if you've got suggestions about other platforms that would be more convenient for you, please let us know, because we're, I'm sitting here and doing my thing, and sort of the bits are getting streamed out to as many places as is practical. So let us know if there are other ones that will be helpful. All right, well, thanks very much.